Okie dokie, what a lovely differential equation we've got for you today. We have dy dx multiplied by d2y dx squared is equal to d3y dx cubed. So to start, we use a substitution. We'll have p is equal to dy dx. So we can rewrite our equation as p multiplied by dp dx is equal to d2p dx squared. And now we can use separation of variables where we've got this dp dx. We'll bring the dx to the right hand side and integrate both sides. So it'll be the integral of p with respect to p is equal to the integral of d2p dx squared with respect to x. So the left hand side, so what we're going to get is p squared on 2, and we'll put our constant over here, we'll have that as a, is equal then to just a single differential of p with respect to x. And now then, we'll multiply by 2 just to make the p squared a bit nicer, and we'll do separation of variables again. So if we have then 2 lots of dp dx is equal to p squared plus, and we'll just leave this as a, it's just a constant, so it doesn't matter, our 2 can be absorbed by that. And then separate the variables again. So what we'll have is that we'll have dp on p squared plus a, and a 2 out the front. And on the right hand side, integrating just dx. So now, when we integrate this thing, the left-hand side, what we're going to get, we'll still have the 2, but we'll actually have an arctan of the square root of p squared, so just p, divided by the square root of a. We'll absorb the square root into the constant though, so it doesn't matter too much. And the right-hand side, we'll get x plus another constant, which we'll call b. So now what we can do, we'll divide by the 2 and take tans on both sides. So we'll have p on a is equal to tan of x on 2 plus b. Just a constant, so again we've absorbed the half. And now we'll multiply by a, to stick that on the right hand side. And now we can go back and use our substitution. So we know p was dy dx. So what we have is that dy dx is equal to the right hand side. A tan x on 2 plus b. And now we'll integrate both sides with respect to x. So y is going to be equal to the integral of tan, which is the natural log of sec, but what we can do, we can say it's like the natural log of cos instead. Just a bit nicer having a cos instead of a sec, because it can just be absorbed inside the constant at the front. So we'll have a natural log of cos x on 2 plus b, and then plus another constant, c on the end. And that's our final answer, spot on. But what we can do instead is write that constant as log of c. And now if we use the log laws, we can rearrange the first term to put a as the power, so the natural log of cos to the power of a of x over 2 plus b. And our log of c, we can combine again into one single log, so having the c at the front there. So what we end up with is our final answer is the natural log of some multiple of some power of cos of x on 2 plus some constant.